These are the lesson 1.5 activities for differential equations. Consider dy dt equals 3y to the 2/3. Discuss existence and uniqueness for solutions with the initial condition y of 0 equals 0. So that means we have to check two things. We have to check the hypotheses of the existence and uniqueness theorem. We have to check is f of ty, that's the right-hand side of the differential equation, 3y to the 2/3, is that continuous at the initial value? If yes, a solution exists, and if no, no conclusion. So f of ty equals 3y to the 2/3. There's nothing about this function that would make it discontinuous, right? There's no negative under a square root. There's no 0 in a denominator. There's nothing in here that would make it discontinuous. That's a cube root, which means you can take a negative, but what I'm interested in is the value 0, when y is 0 and t is 0. There are no t's in there, so I just put in a 0, no problem, it's continuous. So 3y to the 2/3 is continuous at t equals 0 and y equals 0. That's the initial condition. That tells me we have existence. A solution exists with that initial condition. Okay, then part 2 is where we look for uniqueness, and I take the partial with respect to y of 3y to the 2/3. So that would be, you bring the 2/3 down, and you get 2y, 2/3 minus 1 is negative 1/3. And that is 2 over the cube root of y. And I actually can't plug in y equals 0, right? The initial condition is t equals 0, y equals 0. No problem with t, but I can't plug in the initial condition here. The function does not exist. So it is not continuous. Not continuous at t equals 0, y equals 0. So my conclusion is no conclusion. I can't say whether or not there is a unique solution. It's not guaranteed. There still could be a unique solution, or there could be more than one. All right, so next I'm supposed to find equilibrium solutions for the differential equation. So you find equilibrium solutions by setting dy dt to 0. So divide both sides by 0. Raise both sides to the 3/2. And we get y equals 0. So there's my equilibrium solution. Does it satisfy the initial condition? Y of 0 equals 0? Yes, because y always equals 0. Okay, now we're supposed to solve using separation of variables. So we have the equilibrium solution. Now I'm going to find a more general solution, and that satisfies the initial condition. So get all my y's on one side. So I have y to the negative 2/3 dy equals 3 dt. So I just divided both sides by y to the 2/3, and I multiplied both sides by dt. Integrate, integrate. This is just the power rule. So add 1, and I get y to the 1/3. Divide by your new exponent, which is the same as multiplying by its reciprocal, equals 3t plus c. I'm going to solve for y, divide both sides by 3, so y to the 1/3 equals t plus, technically 1/3 c, but that's just a new arbitrary constant, and then cube both sides. So I get y equals t plus c cubed. Plug in the initial condition, 0 for y, 0 for t, and I get c cubed is 0, so c is 0. So my solution is y of t equals t cubed. That was my equilibrium solution. 3y to the 2/3. Now we're going to sketch our solutions from part B on the slope field. So in part, okay, so my equilibrium solution is y of t equals 0. So I've got equilibrium solution y of t equals 0. And then part C was y of t equals t cubed. So that also has the same initial condition, 0, 0, but the solution is t cubed, which looks like that. And you can see it is following the slope field. Okay. So we see that the solution through 0, 0 is not unique, right? In this case. Why doesn't this violate the theorem? Because if you remember, we checked that the partial with respect to y of y to the 2/3 is not continuous at the point 0, 0, so we are not guaranteed uniqueness. And in fact, we don't have it in this case. There are two solutions through that initial condition. So one great consequence of the theorem, the existence and uniqueness theorem, is that when uniqueness is guaranteed, because the partial with respect to y is continuous at the initial condition, no two solutions can ever occupy the same place at the same time, like they do in the example above. So in practical use, we know that for any reasonable differential equation, you will never cross equilibrium solutions. So we've been working under this assumption for the past couple of classes without even realizing it. It's a good thing that we've now verified that our instinct here was correct. Nearly all differential equations in this course will be reasonable enough to guarantee uniqueness, and solutions will never cross. Okay, consider the ODE dy dt equals 1 plus t squared over 1 plus y squared with the initial condition y of 0 equals 0. Show that y of t is a solution. Okay, so I need to just plug in for dy dt and for y. So y of t equals 1, then dy dt, y of t equals t, then dy dt is 1. So I'm going to put a 1 in for dy dt. And then I have 1 plus t squared over, then I'm going to replace this y right here with t, because y of t equals t, over 1 plus t squared. That is true. Okay. And let's check that it satisfies the initial condition. Y of t equals t, then y of 0 is 0. Check. We satisfy both the differential equation and the initial condition. Prove that y of t is a unique solution. So to show that it's unique, we have to show that the partial with respect to y of the right-hand side of the differential equation is continuous. So I'm going to take this derivative, show that it's continuous. So I could use the quotient rule, or I could rewrite and use the product rule, which I think I'm going to do. So this is going to become 1 plus t squared times 1 plus y to the negative 2. And then I'll have to use the product rule on this. So first is 1 plus t squared times the derivative of the second, that would be negative 2 times 1 plus y to the negative 3, plus the second, 1 plus y to the negative 2, times the derivative of the first, and the first has no y's in it, so its derivative is 0. So that whole term goes away, and I am left with negative 2 times 1 plus t squared over 1 plus y cubed, and that, if I plug in t equals 0, and y equals 0, because that's my initial condition, is continuous, right? I have no problems plugging in those values, which means that I have a unique solution. Now consider the same differential equation, but with the initial condition y of 0 equals -1. The solution to this guy can never get bigger than the solution to the first initial value problem. Otherwise, two solutions would have to cross, thus violating uniqueness. So on the slope field, we're going to sketch both solutions. The first one is y of 0 equals 0, and we know that the solution there is y of t equals t. So it's just this line. Okay, and then y of 0 equals -1 would be a different solution. It's a different initial condition. So I'm going to try to follow the slope field, and I know that I can't cross the blue line, so it must be acting like an asymptote. Like that. Okay, consider the differential equation dy dt equals e to the t times the sine of y. Find equilibrium solutions. So we set 0 equal to e to the t times sine y. Either e to the t equals 0 or sine y equals 0. This never happens. And the sine is 0 at multiples of pi. So equilibrium solutions at multiples of pi. Now, if we were to have used Euler's method using an initial condition of y of 0 equals 5 and a step size of 0.05, it yields the following plot of an approximate solution. How do we know that this plot cannot be correct? Well, we know that there are equilibrium solutions at multiples of pi. So at about 3, I have an equilibrium solution. And at -3, an equilibrium solution. And at 0, I have an equilibrium solution. And this plot crosses all of those equilibrium solutions, which I should not be able to do because of uniqueness. So how do I know that this plot can't be correct? Because it crosses equilibrium solutions. So it has to be that Euler's method used too large a step size, and I've introduced too much error here. So it's crossing my equilibrium solutions because of too large of an error.